So let's start. We are starting a new lecture today, which is going to be our last lecture. And it's on discretizing ordinary differential equations. So everybody here is in either right now in the class or you already took ordinary differential equation. Even if you didn't, what we're doing in this class is just a very basic introduction. You don't have to know how to solve ordinary differential equations analytically, or if we do actually end up solving one or two, it's going to be really simple. The whole point is that you're going to learn how to solve ordinary differential equations numerically. And so you don't need to know any fancy tricks that you normally go through in ODE class, like separation of variables and whatnot. No, wait, that's PGE class. Separation of variables is a little more advanced topic. But essentially, you don't have to know the tricks how to solve things. We just have the algorithms, and basically some algorithms work better than the others in terms of accuracy. But as usual, you're going to have to learn at least 4 or 5 methods and then complete them. So, if you would like to do some reading on the topic, in Chopper's textbook, we're skipping quite a number of chapters, specifically on integration and interpolation. And in chapter 22, iterative methods is what's covering iterative methods for solving ordinary differential equations. So just to see where are we in the course progress, we have finished all of these topics, last of them being curve fitting, and today we're doing differential equations. We have skipped interpolation. You have possibly seen that on the list of topics that I presented at the very beginning. In integration, if the time permits, I'm going to do a very short overview of integration. Basically, differentiating and integrating is numerical calculus, you could say. Okay? All right, so let's see a motivational problem where I would like to solve my differential equation numerically. So let's assume we have a tank of water, and there's water coming in up here, and that might be something like a flow that is changing in time, and it could be actually quite a complicated function in time. And then it's flowing out here, and the rate at which the mass of water is coming out depends on the height of this column. The larger the weight, the faster it will go. Right? So essentially, I know that I have flow into tank and I have a change of mass coming in, and these are K1, K2, C are some constant that I have those constants, so all I need to do is plug in time t to get this rate coming in. And then I have water flowing out, and this is something that depends on the height h of water in the tank. G is gravity. I do have rho of water. This is density of water. And also cross-sectional area of this pipe. That's something that I have. So I can actually compute the rate of water flowing out using this formula. So then if I'm just wondering how much water do I have in the tank and how does it change in time, change is basically what's coming in minus what's coming out. Okay, so that's a simple mass conservation law. So my dm over dt is dm in minus dm out over dt. So basically I have an equation that gives me the change of mass in time. So I have all of the coefficients. The only one that is unknown is t. So when I put all of that together, okay, I also could actually just look for the height. I can either solve for mass, or I could throw in height in there too. Otherwise, I have to express this in terms of mass. So basically, I know that the mass is simply rho of water times volume. Okay, so it's this area below times h is my volume, times rho gives me the mass. So this is essentially the ultimate equation that I'm solving. When I solve it, I'm going to get h in time. So the way we would actually solve this for a differential equation, we need a starting point. So starting point is something that I measure. So h of 0, I can presume that I have at time equal to 0. And then for time steps afterwards, the way we solve these things, we're discretizing time. So I'm going to say, okay, at time 0, then I'm going to decide on which intervals am I going to solve for. So let's say 0.5 seconds. Time 0.5, time 1, time 1.5, 5, and so forth. Okay? So that's basically finding the solution means finding h at this discrete time interval. Okay? So we use iterative methods to do that. All right, so this is our motivational problem. Now, let's just throw down some definitions before we actually move on with how to solve it. So ordinary differential equations, such as the one before, have a function of one variable, and I might involve multiple orders of derivatives of that function with respect to the variable. In this case, it was time. Okay? So those are ordinary differential equations. Depending on the order, I need some boundary conditions, and I could either have initial value problem, for instance, this problem from the previous slide, if I give it the initial height at time is equal to 0, that together with the equation is enough to solve the problem fully. Otherwise, I don't have a solution. It's kind of plus minus a constant, you know that. So that specifies an initial value problem. I might also have some boundary value problem, and there is one that we already introduced already. So if you remember that heated rod, okay, heat equation, that heat equation, for instance, you give it values on the boundaries of the rod, and that's a boundary value problem. And in that case, we had a second order equation. This was a spatial variable x along the rod. Okay. So for the second order equation, I need two boundary conditions in order to solve. Okay. So it depends on the order, how many boundary conditions do I need. Okay. So order refers to the order of derivatives that are involved. You could have first order, such as very simple one here, and second order. Now some of them are very simple. So for instance, this one, you don't need any numerical method to figure out how to solve this. Okay. You just go and integrate, and given the boundary conditions, you will find the solution. This one, however, it has, just like as the one before, it has y on this side, and it has y over here. Okay. So we could attack this one by throwing everything that deals with y on one side, everything that deals with x on the other side, and try to attempt solving that way analytically. But as this part becomes more complicated, I could have, for instance, sine of y here, or exponential of y, or it can get more and more nonlinear. Then essentially, I need, at some point, I do not have analytical solutions, and I need numerical methods. As a matter of fact, only a very small fraction of problems that are of practical value can be solved analytically. Okay? So it's actually a minor fraction of those. Normally, we either have very complicated nonlinear functions, or actually have like data. And data in itself does not have to be in functional form. It could be just data. Okay? And you can evaluate it, but you don't have, it's not f of y is sine of y. It's not something that has a closed formula. So in that case, and that's something that you can visualize already in petroleum engineering, how you can always just have data. You have just like pressure at the bottom of the hole. Well, it's not a pretty function. You can fit it with functions, we'll learn curve fitting, but altogether, it's not necessarily a function. So in that case, you will not have a nice linear problem to solve. Okay. So that's basically motivating numerical solutions. And finally, partial differential equations. Basically, there's an example which is essentially, this is in terms of pressure here, but it's essentially the same as this heat equation. It's just solving a problem that is two-dimensional. Okay? So in that case, this is so-called Laplace equation. In that case, we have partial derivatives. So not just this P is a function of x and y, and I have essentially partial derivatives involved here. Okay. So those are my differential equations, just some definitions. Okay. So we will start with simple initial value problems like the one that I introduced at the beginning. In general, class of methods are so-called Runge-Kutta methods. So we are solving an ordinary differential equation, and its general form is dy over dx is f of xy. Okay? So x is my dependent variable, and y is the function that I'm solving for. So one example was right here. Another example is this. I have h and t. So this is, if I divide by rho a tank, then I will have dh dt is some function of both t and h, and the rest are constants that I know. Okay. So both of these examples fit into this general formula. dy is equal to dy dx is equal to f of xy. Okay. So the way Runge-Kutta methods work is that I have an iteration. I know how to do for loops. I know how to program this really quickly. Okay. So every time I start from my initial point that I actually have given in the problem, because it's initial value problem. Okay. So at x is equal to 0 or whatever value I have with, I start with that value. And then my new value is always the old value that I have times slope times step size. And step size is this. I have to decide how to discretize over points that I'm solving. So if I start from x is equal to 0, I can decide that my step size, and we will often refer to it as h, my step size h is 0.25. Okay? So after 0, my next one is 0.25. Okay? And then there is slope. And what is this slope? Well, as usual, the simplest way to do anything is to linearize. So this is my general function. Okay? So I have this some general shape. But here, I approximate this function with a tangent to it at this point. So if this is my slope here, step here at xi, this is my old value. Okay? I figure out what the slope is. I'm calling it phi, and that slope phi will take me to this value as an approximate solution. I can see that this is a first order approximation. Okay? In this particular case, I will get that this is my new value, and I'm kind of quite far away from the actual value of the function. That's because I simplified it too much. But this can work. The hope is, in all of these methods, okay, well, this h is maybe too big. Okay? So if I actually reduce my step size, and let's say that my step size is this much, okay, then I'm not that bad. Then this slope will take me to this as a solution, and I'm not that far away from the actual function. Okay? So in all of these iterative methods, that's called convergence. If I reduce h, I expect that my method will become more and more accurate as I have smaller steps. Now, of course, I want methods that will get there faster with larger h, but I still hope that every time I reduce the step, I'm going to get closer to the solution. Okay? So again, this method that I just described with the first derivative is called Euler's method. Okay? So I'm going to, my phi, if you remember, the formulation of the problem dy dx is f of xy. Okay? So basically this slope is dy dx, and I can simply get it by evaluating f of xy. So that's what I'm going to do, and that's my slope. Okay? So this phi at the current value of xi is simply, essentially, yi is just simply the value at the current step. So I'm just going to say, yi, this is my old value, this is my slope, f of xi, yi. I just evaluate my function as given, times my step size h. And that gives me my new value, yi plus 1. Okay? So I have certain prediction. I'm off from the true value. I just hope that I'm not off by very much. And I'm making certain error here in prediction. Okay? So this is very easy to calculate and very easy to iterate. And I might get, for instance, something like this. So I started from from x is equal to 0, and my step size was 0.5 in this particular example. And I see that this slope can take me quite far away here. Then I'm going to, again, for this value, I can still calculate slope. Okay, that slope takes me to this next point. At that value, I can still calculate slope. Slope takes me to this value, and so forth. So I can actually, in this particular case, I can construct this just by drawing. Okay, I have slopes, and I can just keep going. Now, what is the error that we are making in this? Okay. So did I mention that Taylor's formula is one of the most important ones you need to remember from calculus? I think I said that already. Well, here we come again, Taylor series. Okay. So I know that in general, if I have two neighboring values of the function yi plus 1 and yi, I can write this as yi plus 1 is equal to yi plus f of xi yi h, plus then I have a second order term times h squared, all the way to however many derivatives I can actually compute for this function. Okay. And when I stop, then I have some order of h to n plus 1 error. Now we can actually see that this Euler method is nothing else but basically just chopping off, truncating Taylor series after the second term and on. So this is essentially my Euler's method, right? Does everybody recognize the Euler's method that I just introduced? Yes? So this is my slope, f of xi yi h. Here we go, f of xi yi h. So essentially, I showed you the graphical way of what is Euler's method doing, but one could actually just say, well, I just truncated this Taylor series, and that's how I got the method.
Wait, so on the previous slide, you had the graph comparing the predicted versus the true solution, and there's a huge difference. Will the rest of the Taylor series, I guess, correct that and bring it closer together?
Yes. So if I had the rest of it in, it would correct it.
Okay.
It's just that, given the problem, dy dx is equal to f of xy, it would be harder to evaluate this, okay, and so forth. So adding those terms is not necessarily easy, given that all I know about the problem is that dy dx is equal to f of xy. But if I had it in theory, then yes, this is the difference. So the error that I'm making, the error that was plotted in the previous slide, either this one, this true value versus predicted value, or here, every time, okay, I have essentially, that's the error that I could compute it for Taylor series. And that's how one would analyze these methods to actually formally find out what is the convergence and all that. We're not going to go into that, but that's actually how you analyze, you do Taylor series through and through. Okay? That's how you prove that the method is converging and how fast it's getting. And Euler method is the simplest one because I'm keeping only the first term, okay? So I don't have any other corrections. Now, so first time I do this, this is my error. But then after that, I'm working with this approximation yi plus 1 for a yi plus 2. Okay? So I already have error that I'm making from just chopping off, truncating my Taylor series. And then I'm also propagating my old error because I'm working with a value that is approximate value. Because for yi plus 2, I'm using this computed yi plus 1, which has error built in. And then I'm making, again, an error in truncating this series. So basically, there is some error propagation in there. You will have this first, so this is basically formally the term. Okay, this is the truncation error et. And technically, if I actually look at it, when I have small h, this is sort of the dominant term that I need to worry about. Because if I have a very small h, let's say 10 to the minus 3, h squared, is much larger than h to the cube. So any smaller term afterwards I can kind of ignore in terms of the size. So I can think about this error as this. Okay. So that's what I keep propagating. Now that said, this error term still, as my h gets smaller, the error term depends on h squared, so error term will be smaller as well. Okay? So if I have h that is 0.1 versus h that is 0.01, okay, 0.01 will have much smaller error because the error actually depends on h squared. So here is my sort of proof and hope that yes, I'm getting better as I'm getting h smaller. So here is an example for h is equal to 0.25. So if I had h is 0.25 and this is my slope, I wouldn't take the slope all the way to 0.5. I would take the slope only to 0.25. So I'm making a smaller error here than I would over here. Okay. So then after that, I again evaluate the slope. Slope is right here. That slope takes me to here at 0.25, and that's how I'm getting all of these values. Okay. So I always evaluate the slope of the actual true solution, and I just extend it. So as usual, when I just look at all of the errors that I have round-off error as usual, any kind of calculation that I'm doing on a computer. But then I have this truncation by using that formula. I'm chopping off higher order terms, so that I do at every step. And I'm also propagating whatever mistakes I made before, I'm propagating more. So this is sort of our total error that we actually have in this process. Okay. So this error from first step will get propagated further. Okay. So I call this global truncation, which is basically a combination of this local truncation error and whatever I propagated from before. Okay, so this is just to give us an idea what is the error that we're actually making.
So
all right.
The left chart, that's local?
Hmm?
The left picture, that's local, and the right picture is propagation?
Yes. Okay. So this is like in that one step, this is, if you just start, this is the error you make. And you make that repeatedly, but also from every previous step, you're using the old value. So that old value already has some error that you, because you got there using erroneous ways or simplified ways. So that will keep going. All right, let's practice. Here's an exercise. I want you to work with explicit Euler method. Okay? And this is just formula, so you have it handy. And what we're actually going to solve is dy dx is this polynomial here. Okay? And y of 0 is going to be equal to 1. That's my initial value. And this is easy to integrate. And I didn't want you to do it. I just gave you the solution so we don't spend time. I know that you know how to integrate. So we will actually use this analytical solution to verify how well we are doing with our numerical method. So I want you to solve this using Euler's method between 0 and 4. So we start with 0 and step size 0.5. So first I want you, so this is my first, is y of 0 is 1, that's my initial value. I want you to compute the first step by hand, just to see that you understand how this formula works. And after computing this first step by hand, then I want you to program the rest. Okay? So technically with 0.5 we could solve everything by hand, but it's not. The moment you know how to do it by hand, and then after you have a program, you can then use it. So please program it for general H. H should be input. Let me modify this slightly. So H And this first value, x1 or y1 and y1 should be input. Make it a function. And the solution vector y, vectors x, y of values on the interval should be output. Oh, we also need the end of the interval, so let's call it y end, x end, or xn, maybe xn. So this is what I mean, x1 and xn. So where are you going to stop? Yeah. So I want 0 and 4 to be. And as usual, 3 of us are walking around and helping. So analytical solution is there for you to check, to plot and check. Right? So once you return these vectors x and y, you can plot this function at x for all of these x's, so you can see how. Just to give you a visual, something like this. So analytical solution is this. And this is the different ages, you will get different values. The first x value coming along.
So you just plug in the x equation.
Actually, what I actually mean by here is y2. Now that I'm reading it. So you plug it in this formula, right? So you have x1 and y1, they're 0 and 1. And the next value, y2. So your x2 is 0 plus whatever step size you chose, 0.5, right? So that's going to be your x2. Let's put it this way, x2, y2. And then you just plug it in the formula, right? And since we have the analytical solution, then you can see what is the relative error you're making for that first step. So I want you to compute that relative error as well. So what is y2?
So you plug in, so your yi is 1, and then plug in 0,
This.
y times 0.56.
So f of 0, essentially it's just f of x, really, it's not f of x1, is 8.5. And 8.5 times step size of 0.5. Yeah, but 8.5 stays,
Oh,
right? So function f of x y is minus 2x plus 12x
Okay,
squared
so-
minus 20x plus 0.
Okay.
When you plug in 0 in there. Oh, you're looking at the one below. So below is the analytical solution.
Okay. So just be y to
Step size is
y1 plus
Yes, x equals 1.5% and y equals
5.25. Okay, so that's your approximate.
and so that's the y2.
Yes. Now, if you wanted to know what is the relative error, you can plug into the analytical solution. Plug in 0.5 and see what you get as your true value.
Okay, so
So you're saying you first.
That's your true solution. And then you can figure out the relative error.
right.
Okay, so you plug in 0.
Yeah.
Okay.
What's xn?
Okay, so like the first order.
Xn is 4. So Xn is when it's going to stop. You can keep going. You start at 0 and you can keep going. Or don't just keep going.
Okay,
Stop
so the
somewhere.
second order you're getting 0.
So I want it to be an input so you can change it to 5 if you want to. Like in this row it's going to be 4.
No,
Because you just plug in 0.
So Xn is the endpoint.
Oh, times 8.
times 8. Yeah, is the one. Yes, times 8 plus y1 which is 1, it will be 5.
So does y matter? You can't plug in y. Just basically
Because f is just,
it's written in
yeah, there's no y.
you choose negative x of 0 y 0. So that's your first
Okay,
That's when you have analytical solution.
this fxi that refers to the differential equations of ODEs. So normally we think of fx as like but in this case it's
That's just what you said.
So now you have analytical solution. So you can plug in 0.5, x 0.5 into that. And then you can see the relative error in our solution.
No, I mean,
so y prime is x prime. Is that what you did?
Or like, 0 for x and 0 or I guess you just like
Oh, 8.5. No, the things that, but then you also have like
I have posted the
oh,
slides, by
okay.
the way. Some of you have found them. So why do this?
So we get this.
Yeah, I call that Y1. Yes, and this would be my Y2.
Oh.
That's sure. You can keep going. Yes. So this is half of this is 4.5. You can keep going, but I just want you to take this is what I call Y2.
Oh, yeah.
This would be Y3. So you can if you want to. Sure, once you can find the true value. No, it's 5. You plugged in the wrong.
You would start with
now I don't.
It would be that.
So this is so what is the relative error? Did anybody get to the relative error? This here. 4.25 is relative error. Is that percent or what? So what is the analytical solution y of 0.5? That's your y2. That's your approximate solution is 5.25, right? So if did everybody get there? That y2 is, it's 1, which is y1, plus 8.5, that's this function, which is f of xy, evaluated at 0, okay? 0 is my x1, times step size is 0.5. That's 5.25 when I compute that, okay? Now, what is my true solution? Let's call it y true. Is basically this function here evaluated at 0.5. So it's y of 0.5. Use analytical. So that's actually, can somebody remind me what that is? 3.1 something? 187 and so forth. Okay, so basically this minus this divided by this would be my relative error. What is that?
647.
Once again?
0.647.
So it's 64.7%. Okay? So your relative error, oh, hi, I got an email apparently. So it's y2 minus y true divided by y true. So is everybody clear on which values go where? Now if you're clear on that, you can program this as an iterative scheme. So just keep iterating until you're done with all of the values. So given the age, you kind of discretize your interval between 0 and 4, or what we call here x1 and xn as starting and ending points. And once you compute them all, you can stop. So this is basically the shell of the function with inputs and outputs. Now normally you would want a flexible function so that you actually give it function f of xy. So you can either do that outside, program it, or you can just program it directly inside the function. I just want you right now to get the practice. You can prettify it later. Let's get something solving this particular problem.
the relative error of the first one?
Well, it wasn't mine. Somebody else computed it for me, but it's 0.647. So let me quickly check it. So it was 5.25 minus 3.187 divided by 3.187. Wow, high. Yep, 0.647. Is this true value? Did you get this as a true value?
I think it's 3.2187.
2187. Okay, so we can. Okay.
Does it make sense that the relative error goes up and down?
What do you mean up and down? We computed only one. So up and down as in you got the different value, or what do you mean by up and down? Or does it change for your next step?
Yeah, sometimes it'll go down from there.
Yeah, that's. Oh, but except that this is wrong. Wrong function. Minus 0.5. 4 plus 4. Let me just compute this quickly to double check. Yeah, it's 218887. This is probably if you used more
Oh, yeah.
steps here. Okay, so it's 631 here. So let me just. So you can see that yes, it goes up and down. Okay, so here it's actually a little less than it is here. And I guess it depends on how bad is this tangent that you take, how bad of an approximation is it to the actual function. Where does it take you? So that can change locally for a nonlinear function. So solution looks something like this when you actually do plot all of the different h's. There's just your motivation where you need to get at the end of the class. Good to have a visual, like in swimming, you know, you gotta prop your head up and see where you're going. So what is your x? 7.61, which is 0.4. You can do lens space, or you can do that x1 column 8 column 6. If I hit the actual value. So then your x of 1, you would have already there 0, right? And y of 1 you initialize as the value. Portal.
In this case, we're doing two variables, right? We're all doing sort of one, right? So say y equals 2x, right? And y is equal to x. So this specifies that you're going to choose as a variable. At x. Okay, and then 2 times x, right? Okay, I'll just use what I just said. Y. Okay, so let's say I want to solve for what k is at x equals 2, right? Just check that in. Nice. Okay, so
I do this, and then I just put in that one there, and I should solve for everybody. It should really solve for everybody.
no, actually, I never asked that.
Yeah.
Actually, I honestly don't know. It's interesting.
It might not work.
The thing is that what I usually use, I specify the function beforehand, and then I plug in the values there. But I guess
I mean,
see,
you
see.
can compute it like in the regular situation. You just go and so important point here, when you're actually solving this way, at each point, so I discretize my x's, so for instance between 0 and 4, I have 0, 0.5, 1, and so forth. And then I'm computing y values, and I compute that y value only once for each point. Here we computed relative error simply because we knew analytical solution. But in these methods, we're actually not evaluating error and waiting for it to go down. Okay? We're iterating really through the solutions at every point x, but we're computing each of those just once. And this is how we're computing. So we're not going to keep computing until our error goes down. If we want error to go down, we make h smaller. Yeah, that's the way for error to go down. So that's the difference from root finding methods, where we are trying to zoom in on one particular value. Here we are actually computing a number of values of this function on an interval. Is everybody clear? Or did I just talk here and everybody's just like, yeah, whatever.
I'll actually like solve it.
Alright. See you on Monday. Work on this over the weekend.